Hello and welcome to this video looking at the classification of stars. This diagram here is a really important diagram when we are discussing the idea of stellar evolution. This is called the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram displays all of the different evolutionary states of the stars, as we discussed in our last lesson. The axes are particularly interesting. On our x-axis we have the temperature in Kelvin of the surface of the stars, and you'll notice that they go from a high temperature down to a lower temperature. On the y-axis we have our luminosity. The luminosity is a measure of the total energy that is emitted from the star, so taking into consideration the three-dimensional nature of the star. This is something that we'll come back to talk about in our subsequent lessons. But what we can see is that our evolutionary states are collected into these clusters. So we have this belt through the middle in this sort of shape here, which is our main sequence star. Our star, it has a surface temperature of about 6,000 degrees Kelvin, so we'll sit in and around this point here. You can see that the main sequence has such a huge range of different types of stars. You have some very hot, very bright stars, and then you've also got some much cooler and less bright stars down at the other end. Depending on the mass of the star, whether it's smaller or greater than 8 solar masses, the star will then go into its next evolutionary state, which is either the red giant or the super red giant. I might have already shown you a video which talks about some blue supergiants. Just for your reference, they will sit around this point here and not actually within our supergiant belt. You'll notice about the supergiants and the giants that they are much cooler, but they are still very, very bright, and this is because they have such a huge surface area. The other group of stars which is shown in this diagram are your white dwarfs, which are much hotter but not as bright as their size has shrunk right down. An important feature of this graph is the colour scale along the bottom, and actually we can see that the colour of the stars depends solely on the temperature that they're at. We're now going to have a look at what gives them this colour. So, to do this we need to think a little bit about black body radiators. Stars are always described as black bodies, and this means that all of the radiation incident on them is absorbed and isn't reflected. The consequence of this is that when we look at the absorption or emission spectrum from one of these black body objects, we see the full range of the electromagnetic spectrum, and we don't see, like with a discharge tube with a particular gas filled inside it, particular wavelengths coming out. However, depending on the temperature of the object, as you can see by the different curves that we have on this graph here, what we can see is that we have a greater intensity of light which is emitted from particular wavelengths. This means that each of these black body objects will appear a slightly different colour due to the wavelengths that they are emitting. Interestingly, we have an inverse relationship between the temperature and the wavelength. So as my temperature increases, we actually see that the maximum wavelength or maximum intensity wavelength along here is actually getting smaller. Wien's law is then a law to explain this relationship and to give us a numerical calculation that we can complete in order to find the maximum wavelength and therefore identify the colour of the star. Wien's law tells us that the maximum wavelength, my lambda max here, times by the temperature, which should always be in Kelvin, is always equal to this constant, 0.0029. We should note here that this unit is actually meter Kelvin and not millikelvin. So, by measuring the maximum or peak wavelength from a particular star, we can very, very clearly and quickly identify its temperature. This temperature is the absolute temperature of the photosphere. The photosphere is the light-emitting outer layer, or sometimes referred to as the surface of the star. We can't actually directly detect anything about the temperature of the inner core of the star, but we can then infer some of this information from the outside temperature. So we've now linked the colour of the star directly to its temperature, and this allows us to start classifying our stars more precisely. Here is a slide from your course notes which can be found on Edmodo. We're going to have a look now at the spectral classes, and you'll notice that our spectral classes are down the left-hand side of the column here. They go from O, B, A, F, G, K and to M. Now this might seem like a very bizarre order to these spectral classes, but initially they were ordered in alphabetical order due to the colour that the stars appear. After this, it was then realised that actually a better way to order these stars was using their surface temperature, and this has then meant that the spectral classes and the classification order now seems a little bit weird. You can see though that our highest spectral class, the O class, has the greatest temperature from 25,000 to 50,000 Kelvin, whilst our M class star at the bottom, which is a red colour, has the lowest temperature, which is approximately 2,500 to 3,500 Kelvin, so a much colder star comparatively. The colours also allow us to have a look at the absorption spectra, and we do see some specific absorption lines for each of these stars, which is representative of the types of materials that might be present within the stars themselves. So, for the O-class star, these are very hot and bright, and we can clearly see from our spectral lines here that mostly we have some helium, some ionised helium and some hydrogen in these stars. Conversely, as we go down through the classification and the stars become much cooler, we end up with some of these heavier elements that we can see as absorption lines in here. These red and orange stars are normally stars which have gone through their main sequence and now are in their giant or super red giant phases. This means that as a star they have gone through many of the processes of fusion and so have been able to produce some of these heavier atoms. It should be noted here that the absorption spectra that we're viewing in these diagrams is from the corona of the star. Now this is the hot gaseous area which surrounds the star, so it's above the photosphere, above the surface of the star. These absorption lines are indicative of the types of atoms that can be found outside of the star. And these spectral lines that we see here can then allow us to classify the stars even without calculating their temperature directly and looking at their overall colour and blackbody radiation pattern. The information in both this table and for the spectral classes with the absorption spectra is really important for your exam, and you can be tested on this for factual recall. So I would strongly recommend now that you take a note of this table and the prominent absorption lines. This can be just in a written form as in my table up here, because this is information that you will have to learn for next year. You might want to pause the video now to do this. We're going to extend our understanding of this classification of stars using the Balmer series next lesson, and we're also going to begin looking at how to calculate the power of stars and their magnitudes.